Hello, welcome back to the channel. And as you can see, I've got the whiteboard out. So this is going to be a video part of my solar journey and also explain the science of solar panels, batteries and energy. And today I'm going to talk to you about how batteries work. So there's been a huge increase in battery manufacturing over the past decade or so. This is for a number of reasons. One is due to the improvements in electric vehicles. So electric cars use obviously batteries to store energy, which they can then convert into their kinetic energy. People are having them installed in their homes with solar panels, so excess solar electricity generated by solar panel, and the excess can be stored in batteries for later on. In devices such as laptops, phones, there are rechargeable batteries in there. So there's been a big improvement in battery technology. So in this video I thought I'd explain how a battery actually works. So the principle of a battery is that it needs to generate something called a potential difference or voltage. And the way it does that is by generating electrons. So I'm going to mark these as E-. And providing that there is another place where there are less electrons, there could be no electrons, there could technically be holes, but let's just show this as less electrons by just putting one E here, and you put in between these electrons a barrier that the electrons cannot go between, then you've created an effective battery. Because what happens when you connect up a wire, an electron here will go up, move around the circuit to join the electrons on the other side, so that there is an equal number of electrons on both sides to reduce that potential difference. So that's the principle of the battery, that you need to have an excess of electrons on one side, less electrons on another side of a barrier. When you connect it over a wire, those electrons will flow, and if you have some sort of load, then it will power that device. So the question is, how does a battery do this? So we have to go back to some GCSE level chemistry for this. But before that, a battery does not store electricity. What it does, it stores chemicals, or it has chemicals in it. So it has chemical potential energy, which it can then convert to electricity. So the simple way that a battery works is metals have different reactivities. So if you remember back to your school days, you learn about group 1 metals such as lithium, sodium and potassium, and if you put them in water they fizz, they sometimes ignite, so they're heavily reactive. You also know that other metals, something like gold, are non-reactive. So you have something called the reactivity series, and one end you have the group 1 metals, which includes things like lithium, and on the other end you have the materials such as fluorine, which are also reactive, but an opposite reactivity to the group 1 metals. And what I mean by the opposite reactivity is the reason why something like lithium is very reactive is because it has one electron in its outer shell. So if we were to draw it, it would be 2 electrons on its inner shell, and then on its outer shell, 1 electron. Atoms like to have a full outer shell of electrons, so to make this shell full, you'd either have to take on 7 electrons or just give away 1. And giving away 1 is easier, and therefore it has a full outer shell of 2, and the shell disappears. Fluorine is the opposite, it has 7 electrons in its outer shell, therefore it likes to take on 1 to make itself complete or more chemically stable. So lithium reacts very readily and gives away an electron. So when it reacts, what it ends up with is you have a lithium ion, so it still has this outer shell with 2 electrons, but because it's lost this electron and the electron is negatively charged, it becomes a lithium ion with a positive sign to it, so it's positive. You then have a free electron. So if you have a material which chemically reacts to give away this electron, then you can create that excess of electron and that potential difference. So the way they do this in a battery They have a material, which I'll draw in black, and let's call this copper. You put in between it, I'll keep the same colours I used earlier, a barrier which doesn't transport electricity, something like cardboard, and then underneath you can put another material such as aluminium, which has a different reactivity to copper. So copper reacts more readily than aluminium. And then if you surround this in a material like an acid, say even vinegar or lemon juice, what happens is the copper reacts to form salt, but it also generates an excess of electrons. The aluminium will also generate some electrons, but less. So that means when you connect it up, your electrons will flow. So this is the idea of a penny battery. So this is an experiment you can do yourself. There are videos on YouTube where you get a copper penny, like a two penny piece, some card and some tin foil. You soak them all in vinegar, which is the acid needed to generate this reaction. If you add a bit of salt in, it improves the reaction, and you can create this layering system, and you can buy a cheap LED bulb, connect that up, and you can see it light up. So this will generate about half a volt of power. So that's the basis of a battery. So the famous batteries that you have in your car are the lead acid batteries, and the way these work is that you have two electrodes. So I'm not going to use that pen because the pen's dead, so I'm going to use this pen. So we have some lead, which is Pb. You also have another electrode, which is something like lead oxide. I think lead oxide is PbO2. And what you do is you put that in a solution. So if I draw a bottle or a container with a liquid in it of sulfuric acid, which is H2SO4. So, and there's also some water in this as well, because you need water for your acid to dissociate in. But what happens is the SO2 or H2SO4 reacts with the lead to form lead sulfide, which goes to, let's draw it down here, PbSO4, I believe, plus a lot of electrons. So we're creating that potential difference. The lead oxide also goes to PbSO4 plus some water, but importantly no electrons. So this means that in this scenario we now have some excess electrons on this electrode and a lack of electrons on this side, which means that when we connect them up, the electrons will flow from the original lead electrode to the original lead oxide electrode. So that's how the batteries in your car used to work. You can drive this reaction backwards, but it takes a lot of energy and it's not particularly efficient, and also you have a lot of acid in these, so the batteries are fairly heavy. So they were never ideal for large battery storage, which you need for a power electric car or for supporting the grid. If you are just supporting the grid or have a home battery, it doesn't really matter how heavy that battery is or how big it is, within reason. So you can use less ideal materials. Also, if you're supporting the grid or home battery, you want to basically have high energy density. So you want to be able to store a high amount of energy in this, and you want to be able to release a certain voltage from it. So that's the idea of battery chemistry. You can tailor your chemistry of your battery to provide either very high power, so sharp release of electrons, which don't last very long, which is what a car battery does, or you might want it to generate electricity over a longer time, but still at a reasonably high power, something like in a car battery. And also you want the car battery to be light. So luckily, something like lithium is the lightest of the metals. It's only element 3 in the periodic table, so it's the lightest of the metals, it's the third lightest element. It's also very reactive, so it's ideal for using in something like a car battery or a battery that has to be moved. You can also use sodium, but that's slightly heavier, so there is technology now coming around with sodium ion batteries. But the way that a lithium ion battery works is, I'm going to draw lithiums in red, so we're going to have some lithium ions. So by themselves, these are very, very reactive and will readily dissociate. However, if you bond them into a lattice with something else, I'm going to use oxygen. So this would repeat, this sort of unit cell would repeat in 3D. This lithium becomes stable. This is lithium oxide, or basically lithium rust. And this happens to be very, very stable. However, if you put in a barrier, so I'm going to have to draw the barrier in green, and I'm going to speckle it because this barrier has holes in it, which is permeable. And you surround this with an electrolyte. So electrolyte is something that's a salt, so it's got lots of little negatives surrounding it. I'm also going to put some on this side as well. So the blue dashes represent the negative electrolyte salt. So the final part of a battery is, or an lithium ion battery, is over here we have some carbon in the form of graphite or even graphene, which is a hexagonal structure, which I'm not very good at drawing, but it forms into layers, which means that there are spaces between the layers, which stuff can permeate. So what happens is, if you applied a power supply to this, what happens is you start to break down this lithium oxide, you actually give it energy, and some of the lithiums become free. So if this lithium becomes free, it separates off and forms into an ion. So it becomes lithium plus, and you get an electron. So the important thing is that this electrolyte is full of electrons, or is full of negative charge. So this electron doesn't like to be in it, and it means it can't go through this green barrier. The lithium, on the other hand, can go through, and therefore gets captured in the carbon. Because we have a power supply, so I'm just going to draw it a power supply, it's going to be an AC one. This electron ends up moving around the circuit and coming into the carbon graphite side. So we end up with a lot of electrons over here which are separated from their lithium. And we also have some lattice over here. So this is charging the battery. So that's one of the advantages of lithium batteries, they can be charged multiple times. What happens then is when we connect up a load, let's make it a light or something like that, these electrons, there's an excess of electrons on this side, so they get pushed back around the other way, goes through the load, and therefore powers your device. Your lithium also works its way back, so the lithium now moves in the other direction and forms back with the lattice. So this is the idea of how a lithium ion battery works. So the chemistry has been moving on to create higher energy density. So now you can get things like lithium iron phosphate. So the iron, on this side, instead of lithium oxide, you can have lithium ion and phosphate, which is meant to be more energy dense and breaks down easily. So this is where the chemistry moves on to. So as far as the developments of batteries go, they are trying to use less lithium because it needs to be extracted from the earth. I think Australia are the largest producers in the world at the moment, and then it needs to be refined. Meanwhile, something like sodium could replace the lithium in stationary batteries, and sodium can be easily extracted from the sea. There's also a lot of research being done into these graphites to make those more perfect for holding the electrons and the lithium. So they're starting to use things like graphene because this has a higher surface area and is thinner and therefore lighter. So anyway, hopefully that explains to you a bit about how a battery works. If you've enjoyed this video, please hit the subscribe button, and I'll see you in another video soon.